Thank you, everybody. Good afternoon to you all. I am Sampa Akter, PhD student, University of Connecticut. Today, me and my team member Meshach will be presenting pyrrhotite oxidation, insights into laboratory testing of concrete, expansion and deterioration, and the acceleration of reaction rate. This is the outline of today's presentation. I will be presenting factors affecting iron sulfide oxidation in concrete. The goal of my presentation to determine the factors that speed up iron sulfide oxidation and understanding and quantifying deterioration. For this purpose, I have selected several types of iron sulfide bearing aggregate. As you can see in table 1, their total sulfur content and mineralogy. Initially, I have selected 4 sulfide bearing aggregate, 2 from Connecticut, CT1 and CT2, and 2 from Canada, CA1 and CA2, as you can see here. And however, the expansion obtained using these 4 different types of sulfide bearing aggregate are very low. That's why I have selected pyrrhotite rock having total sulfur content of 25.5% to better understand the mechanism within reasonable time period. Here figure 1 shows the factors and testing condition I will be discussing today. And the mix idea, I have identified each set of mix as per their mix ingredients and exposure condition. To maintain constant temperature and humidity, I have used environmental chamber, curing room setup, also oversaturated salt solution. Here figure 2 shows the length change of mortar bars cast with 4 different types of sulfide bearing aggregates, including contour aggregates. Within 280 days, they only showed less than 0.03% of expansion, which is very low. However, the expansion obtained using CA2 aggregate having total sulfur content of 0.79% in the mix showed comparatively higher expansion than other 3. Therefore, with the amount of sulfur content, the expansion is increasing. So another parameter, water cement ratio, as you can see in figure 3, the length change of mortar bar for increased water cement ratio of 0.75, while the other ingredients were same as I discussed in figure 2. With the increase of water cement ratio, the expansion did not increase, rather it showed higher shrinkage than the mortar bars cast with 0.6 water cement ratio. Effect of relative humidity between 95 and 100%. Here in figure 4, 3 sets of mortar specimen, F1, F6 and F5, they are cast with pyrrhotite rock having total sulfur content of 25.5%, but the total sulfur content in the mix is 6.91%. 2 specimens, F1 and F6, they were exposed to a 95% humidity condition and 23 degrees Celsius temperature. And they started cracking after 85 days. However, F1 specimen continuously kept under the same environmental condition, and it showed quickest expansion and completely broke after 147 days. It also showed 19 millimeter deflection. Another specimen, F6, transferred to 5 degrees Celsius temperature to promote thaumasite formation after 110 days. It did not show any further expansion or cracking. It could be due to the absence of carbonate mineral. And specimen F5 kept underwater at 23 degrees Celsius and 100% humidity condition. It showed very slow expansion, only 0.04% after 230 days, and no cracking. Another important parameter, sulfate generated over time, was determined using WD-XRF method. Here you can see F1 specimen exposed to 95% humidity condition and 23 degrees Celsius temperature. It showed highest sulfate generation over time. It also showed the highest expansion and completely broke after 147 days. So that means a good correlation was found between expansion and sulfate generation over time. Another two parameters, as you can see in figure 6 and 7, compressive strength and dynamic elastic modulus are determined for the same specimen discussed in the previous slide. Here also a good correlation was found. F1 specimen showed significant decline in compressive strength as well as in dynamic elastic modulus. On the other hand, specimen F5, which kept underwater, did not show any compressive strength loss or dynamic elastic modulus loss. Rather, it showed a slight increase of compressive strength and dynamic elastic modulus. Effect of concrete cross section. Here three specimens, mortar bar, cube and cylinder, cast with the same ingredients, but their cross section was different. Here a mortar bar having the lowest cross section of 25 by 25 millimeter showed fastest cracking before 3 months. On the other hand, cylinder specimen having the highest cross section of 75 millimeter showed delayed cracking at 10 months. Figure 9 shows the effect of air entrainment. With the increase of air entrainment, the expansion is decreasing. It could be due as with the air entrainment, the permeability of concrete decrease. Effect of sulfide bearing aggregate size. Here in figure 10, F1 specimen cast with fine particles. It showed quickest expansion and broke completely after 147 days. On the other hand, D2 specimen cast with same amount of pyrrhotite rock, but the particle size was bigger, and it showed only 0.01% expansion after 100 days. Because smaller particle sizes, higher surface area correspond to higher sulfur content. Another important parameter is the temperature. Here 4 specimens exposed to, in figure 11, 4 specimens exposed to 4 different temperature conditions. With the increasing of temperature, the expansion is increasing. Here D4 specimen exposed to 80 degrees Celsius temperature. It showed the highest expansion and started cracking after 73 days. On the other hand, D1 specimen exposed to 5 degrees Celsius temperature, it did not show any expansion, rather it showed only 0.04% of shrinkage. Effect of the type of iron sulfide. I have selected 2 type of iron sulfide, pyrrhotite rock and pyrite. Here a specimen F1 cast with 40% pyrrhotite, and it showed quickest expansion and completely broke after 147 days. And this specimen F12 cast with same amount of pyrite. It showed very slow expansion, no cracking, only 0.046% expansion after 240 days. Another 2 parameters, compressive strength and sulfate generated over time are also determined, and they showed good correlation with the expansion. Here pyrrhotite showed the highest expansion, the specimen F1, and it also showed the highest decline of compressive strength, and this specimen pyrrhotite showed the highest sulfate generation over time. So galvanic interaction, we know when 2 sulfide mineral come in contact with each other, galvanic interaction occurs due to the differences in their rest potential. Here specimen 1 cast with 40% pyrrhotite only, and specimen F15 cast with 40% pyrrhotite plus 15% pyrite. It showed cracking before 20 days than F1 specimen. It could be due to the galvanic interaction. Galvanic interaction also accelerates the oxidation. The conclusion from my limited study: expansion, concrete compressive strength, dynamic elastic modulus, sulfate generated over time can be measured to quantify concrete damage caused by iron sulfide oxidation. These 4 parameters showed an excellent correlation, and concrete specimens with smaller particle sizes, less air entrainment, smaller cross-section exhibited the fastest expansion and cracking due to iron sulfide oxidation. Also, oxidation rates increases with increasing pyrrhotite content, galvanic interaction, and temperature of 80 degrees Celsius. And between 95 and 100%, 95% RH showed the greatest expansion, and pyrrhotite exhibited almost 100 times higher oxidation than pyrite. Thank you. Now, Meshach will present the rest of the part.
Thank you, Sampa. Hi, everyone. I'm glad to be here to present my research. So, Sampa has presented the first part, and for my aspect of the presentation, I'll be talking about electrochemical acceleration method we used in accelerating the whole deterioration process as well as the oxidation in concrete samples containing pyrrhotite aggregates. So I'm actually glad that the presenters as well as Sampa have talked about all of the problems happening in Connecticut, in Massachusetts, and also some parts of Europe. So I wouldn't be talking much about that, but in all of these problems, one thing we've seen is in Connecticut, for example, it takes about 10 to 20 years for these structures to show signs of damage. And also, this should be about the same in Massachusetts, but then the fastest is in Canada. We have also read literatures where in Canada, especially the Quebec region, we've seen this deterioration in about 3 to 5 years. So now that brings us to 2 main problems in my research. The first is, Liana presented something, one of my colleagues from UConn. She said this whole process is interconnected and complicated, the whole damage mechanisms. An example might be when she said, having pyrrhotites does not mean damage, and also having a high sulfur content does also mean, and also not having pyrrhotites does not mean this sample will not be damaged. So it's complex. We also do not know how the pH and some other factors affect what's going on in all of this deterioration process. And secondly, considering the time frame, especially when you look at Connecticut alone, 10 to 20 years, that's a long time. So conducting such a research would take a huge amount of time. So what I really wanted to do is find a way to identify and define these damage parameters and also investigate and verify the damage parameters of samples in comparison with field conditions. That's the damage we also experience in the field as well through an acceleration method. Now, this method has been going on for about 2 years, and what I'll be sharing right now is just a snippet of what we've been doing over time. So for this, my presentation, we'll be looking at how the voltage magnitude affects the duration of the sample, and also will be how we evaluate this damage. So we are using a non-destructive method, which is resonance frequency, and also looking at the cracks. We estimate the crack length. Now let me talk about the whole mechanism behind my acceleration method. So what we did is we drove chlorides. Chloride ions were the catalysts we used in this acceleration process. So we drove chlorides into the concrete samples through a method very similar to what we have in the rapid chloride penetration tests. It's something very similar. So when we drove chlorides into the samples, oxidation and cracking occurs, and then we found a way to assess this damage over time. Now, cracking might be the best way to see damage in concrete samples, but also we need to find a way to know if something is going on in there, even when we do not see crack. We have 10 to 20 years in Connecticut. We know some sort of reaction are going on in there, but the only way we know this damage is when we see crack. So resonance frequency testing was one of the methods we came up with. And also we took pictures, put these pictures side by side, traced the cracks, and then we found a way to estimate the crack length of these samples. Now the next thing I will do is I will explain our test setup. I said something earlier. I said this was, we built the setup with the principles laid down in the rapid chloride penetration test, and we know there are 2 main methods for this, which is the STM standard as well as the NT-Build 492. Now for the ASTM standard, we have 60 volts being passed into a setup where we have two brass mesh electrodes, and we have a 2-inch diameter sample in there. A 2-inch length sample in there. And also the NT build is also somewhat similar, just the configuration is different. But one major difference is for the ASTM standard, we have 60 volts being passed into the sample for a 6-hour period. And also we have a 3% NaCl solution when we talk about the concentration. But for this, we have, so the voltage and the time depends on the condition that you want to run. There are a lot of things that actually affects the current passing through the sample as well. And also we have about 10% chloride concentration in here as well. So this is our test setup. We have 2 HDPE sheets of 4-inch thickness, and we have a 3-inch cylinder, concrete cylinder, sandwiched between those 2 HDPE sheets. And also we used graphite electrodes because of their stability in chloride environment. We were trying to avoid corrosion because we'll be running this for a very long amount of time. And also for electrolytes, we use sodium chloride, 10%, similar to what we have in the NT Build 492. And also our sodium hydroxide, also 3 molar for this experiment. To put these setups together, we use an 11-inch, 4 11-inch 18/8 stainless steel rods and 8 knots. They were fastened by 8 knots as well. So these are pictures of the setups. And now, these are the samples we used. For creating our samples, these are the materials we used. Now, we sourced these aggregates from the Quebec area in Canada. And why we use the Canadian aggregates was because, like I said earlier, this takes about 3 to 5 years to show signs of damage in Canada. So this, we wanted results really fast. And since this was fast, we were sure that if we could accelerate this, then also we'll be able to get faster results in our setups as well. Now for our control aggregates, we sourced these rocks from a quarry very close to campus at the Yukon. And we also did total sulfur testing on them as well. For this, we used the LECO elemental analyzer described by my colleague. And we got the total sulfur to be 1.7%. For the control aggregates, this was 0.04%, which was fine, which is within the acceptable limits by most of the guidelines proposed. So these are the molds. We sucked the samples, and then we ground the cylinder to have a flat surface so we could have them in our test setups. We wrapped them in plastic sheets, and finally we had them in the test setups and had them running. We ran 3 samples. One was run at 15 volts, 25 volts, and also 35 volts. We wanted to know how the applied voltage affected deterioration rates, if this would have an effect on the rate of deterioration as well. So I'm only showing the 35 volt samples here. After 35 days, this was what our sample looked like. You can see the body of the cylinder right here, and also these are the faces. This was the face we have on the sodium chloride end, and this right here was the face we had on the sodium hydroxide end. So for the sodium chloride, you can see signs of oxidation in there. And also the sodium hydroxide, you can see the matrix being eaten away. Now, one of the reasons why this might be happening is because we know that when iron sulfide oxidizes, sulfate is being released into the concrete. And also hydrogen is released, sulfuric acid basically, hydrogen has the protons, and also sulfates are released into the concrete. So the protons migrate to the sodium hydroxide end, and we believe hydrochloric acid is being formed on the sodium hydroxide end. And hydrochloric acid, we know it's been used to separate aggregates from concrete matrix. So we believe that's what is actually eating up this aspect of the matrix. But further studies is still going on into this from our material side, and very soon we'll have clear answers for this. Now, this is our control sample. We also ran this at the same conditions, 35 volts, which was the worst condition. We ran them, and this was also for 35 days. We did not see any form of cracking in the sample, which was good. And also, this was the sodium chloride phase and the sodium hydroxide end. Now, but one thing we wanted answers to was the sodium hydroxide end here showed the matrix being eaten up. But for this part, we saw that the matrix was not being eaten up at all. But a close visual examination showed that something was going on in there. So just to be sure that the pyrrhotite add an effect like sped up, accelerated this process, we allowed our control sample to run for 84 days. And now we can see that its control sample is also having similar features with this. And now we can tell that the presence of pyrrhotites in there actually accelerated this process as well. Now also I mentioned, so we also took field samples just to compare what we have. So we took cores from field samples, like from foundations in the field, Foundations we were sure had pyrrhotites in there and were currently experiencing damage due to pyrrhotites. And we also ran these samples in our setups. Like what we had in the previous picture for the lab samples, we also saw this same deterioration in the field. In fact, at some point the matrix was eating up and we also had to reduce the height of this sample. So we started with 6-inch. It got so damaged, we had to slice the face and we got this and we kept on running our sample. So this was at day 56 and this is now 4.5-inch because we started at 6-inch and these were the faces of the samples after running for 112 days in our setups as well. Now, we also used a non-destructive testing method, resonance frequency. This is ASTM C215. We used the transverse mode for this testing to just know what's going on over time in our samples. So we tested every 7 days, but I only just show for this table, I only brought results for the 0, the 14, and also for 35 days. So you can see we started at, so we also got the dynamic elastic modulus using this equation. So this is from ASTM C215. It's the standard for resonance frequency testing. And so what we got was, on day 14, now you can see for the 35-volt samples, the resonance frequency had dropped from 12,000 to about 9,000. Same with the dynamic elastic modulus. For 25 volts, it was also a drop, but not as much as the 35 volts. And also the same happened for the 15 volts. But now, if you look at our controlled sample, that's the M41C, the last one on this table, you discover that there was no significant drop in either the resonance frequency as well as the dynamic elastic modulus. We plotted the curves here. So this is for the 35 volts. It's obvious that the drop was the largest. And also this was for the 25 volts. And this is for the 15 volts. And up there, the yellow line we have there, that's for our controlled sample. So we did not see any damage in the control sample. And this was an indication that the pyrrhotites contained in the mix or in the aggregates used for making this specimen or the concrete foundations was the main reason why we have cracking and also deterioration in the samples. So now, in conclusion, employing the adopted electrochemical method effectively accelerated the oxidation and duration of laboratory casts and also field samples. And those are shown in our results, some of the pictures I presented in the previous slides. So as exposure time to accelerated oxidation increased, the resonance frequencies and also the dynamic elastic moduli in the pyrrhotite-bearing samples and field samples also declined. And while the control sample remained stable, showing no measurable sign of deterioration in our control sample. Higher applied voltages were directly associated with increased oxidation and also increased deterioration rates, and greater reduction in RFs and E's were also correlated with the samples having higher voltages. That's the one having pyrrhotites in them. And now finally, these findings will help us in understanding the oil damage evolution, as well as allow us to evaluate potential risks of concrete failure. And this method will also be critical for the study of potential mitigation strategies, which we are also working on right now. One of our PhD students is working on this, and also help towards the stability and longevity of residential concrete structures facing this problem, maybe in Connecticut, in Massachusetts, and also some parts of Europe as well. So that's all for my presentation. Thank you.